All right, I kind of want to just talk through example 6.3 from the notes. So this is our first model, model 1, where we have a bar of length L and the constant C, which depends on the material of the bar. We're just setting equal to 1 just to keep everything looking simple for now. Therefore, the way the heat equation is of this form, where C is 1. The initial temperature distribution, we're assigning the function x times x minus 1 for x between 0 and pi. And our boundary conditions for model 1 are that there is no energy flowing in or out of the endpoints of the bar. So all the energy inside the bar at the moment in time when the external heat source is kind of heating up the bar into this initial temperature distribution is turned off, and then those external kind of heat sources at the endpoints also act as insulators. So once they're turned off, they don't allow heat to flow in or out of the endpoints of the bar. So all the energy at time t equals 0 that's in the bar is trapped in there, and no more energy is actually coming in or out. From our general solution, without any boundary condition specified, we had a series like this, except it also had some terms added to it, b sub n sine nx as well. So what we realized was when we differentiate this function in the x variable, all those sine terms turn into cosine terms. And when you evaluate those cosine terms at the ends of the bar, you don't get 0. So in order to force the boundary condition to hold, we just said, well, let's assume that the b sub n's are all 0. So we have a bar of this form. Because when we differentiate these cosine terms, they'll become sine terms which always equal 0 at the ends. So this condition, this boundary condition, is satisfied by this format. The only problem that introduces is it forces us to plug in t equals 0 and get a Fourier series of a 2 pi periodic function in this case, which has to be equal to our initial temperature distribution restricted to the interval from 0 to pi. So just like we did with the vibrating string, where we needed an odd extension to make the boundary conditions match up, we used a sine series. We're using now a cosine series because we have to because of these boundary conditions. So we're actually thinking of an even function, which is equal to our lowercase f of x, highlighted here, and then computing its Fourier series coefficients, which we can compute in the following way, just by using our actual function x and only integrating from 0 to pi. So a0 is basically the average temperature along the bar at time 0, and that's constant in time because of the insulation at the ends of the bar. So this constant is equal to the steady state temperature at every point along the bar. So over time, this solution of the distribution of the temperatures across the bar will converge to the horizontal line, whose height is this number a0. So at every time t, you can see in the graph that the average height of the graph is constant as it's slowly or quickly, depending on c, converging to the steady state distribution, which is just a constant function or a horizontal line. So we also have to compute the coefficients. Again, we can do all this with these simple functions in some software, get a formula here, and then when we sum our series to some large number of terms, capital N, that's the approximating function. So the error is the terms that we're kind of deleting. We want to make sure we're deleting something that's uniformly small. So again, we have our simple uniform estimate is just take this error series and estimate it above in the easiest way possible, which is just bring the absolute value inside the sum, bound the cosine terms by 1, above by 1, and then bound the coefficient in absolute value by some constant over power of lowercase n. In this case, the numerator here does not have any factors of n in it, or any powers of n. So this is a number, but it changes as n changes. We just want to estimate that above. So we have a 2 times a bunch of stuff in parentheses, but we just look at each term individually and just take the absolute value of each term individually and add those up, because that's going to be a necessarily bigger number. And that's where this 4 plus 4 pi comes from. So we get a 1 here plus a 2 pi here when we take the absolute value, plus a 1 here when we take the absolute value. So in the parentheses I have 2 plus 2 pi, multiply the 2, distribute the 2, and I get the 4 plus 4 pi. And the denominator is already positive, so pi n squared on the bottom. And this is the form that we wanted to use our power formula whenever you do have a series that is like, basically acting like a series where it's some constants times the power of n. So in that formula we have our constant is this 4 plus 4 pi all over pi, and our power is 2. So when we actually plug in, we get this general formula. So given the error epsilon, we just plug our epsilon into this number, we get a number, and then we just choose the smallest positive integer n that's bigger than that number. So again, in this case, we see that if epsilon is 0.01, we could use 528 terms, and if epsilon is 0.1, we could use 53 terms. Now in our graph, this graph is not to scale. As you can see, the horizontal is from 0 to about 3.14, which is pi, and the vertical is 0 to 6 or 7. So the real graph is a little bit more vertical than this, stretched vertically. So we'll see that in the animation. What you can see is the initial temperature distribution in red over time is flattening out. So we're going to go ahead and use 53 terms. Our error of approximation is going to be 0.1. What that means is the graphs that we're seeing may be off by a vertical distance at every x, at most 0.1 units, but again, 0.1 units on this vertical graph from 0 to 7 is very small visually to see, so we really won't be able to tell the difference between the animation and what would be the true animation if we actually could graph the entire infinite series for our function. Let me just go ahead and do this, just show you. Again, with Maple, this is nice. You can kind of do everything in one place. So again, I'm just telling Maple to access certain tools for creating the animation, and then I'm defining my length, my value c, and my function for the initial temperature distribution, and then I'm calculating my A0, and I'm defining it and assigning that value to the number A0 here. And then I'm doing this separately just to illustrate to you what the formula looks like when we compute it. And again, I'm using m here instead of n because I'm using n below in the formula. And in Maple, once you use some label for something, it has values, so it can be a problem to use it more than once. So I'm just using a different, I'm going to use m instead, just for the formula purposes. So that's just to see the formula, but in reality, we don't really need that. We wouldn't really need that formula. We would just need to know how many terms we need, and then this loop here is just computing and assigning all of those coefficient values, a sub j, for 1 up to 53, so that I can call on those coefficients in my formula down here for u. It's not really u, it's the approximating function, u sub n, which only has the first 53 terms in it. All right, so let me go ahead and run this. Let me also do one other thing here. So let me go ahead and run this Let me go ahead and do one more thing here. In this integrate, we have the formula already, but for the graphical purposes, let's actually evaluate the decimal of that. In Maple, that just means evalf, just means evaluate the floating point number. So it gives you a decimal instead of the number with pi in it. So again, in our animation, we're basically animating a bunch of graphs of our solution, approximate solution, from 0 to L. We're doing it for 4 units of time, which will basically be seconds for us. And the frames is just how many frames we want. So the default is 10 frames per second. I can always change that, but I just multiplied 4 by 10. And the scaling constrained means the graph will be shown with equal scale on the vertical and horizontal, so it's a realistic depiction of what the temperature distribution functions look like. Again, we have our A0 computed as about 1.72. The formula is what we saw in the notes, except I have an M instead of an N in it. And then this is just telling me that I did define the function to have the form that we want. And all the numbers for the coefficients are stored in these symbols A0 and A sub n. So just run the animation, we'll see that the steady state temperature distribution will converge to a horizontal line, and the height of that line will be this A0, about 1.72. That's only 4 seconds, so after 4 seconds it means it's already pretty close to that steady state, but it will take more time to basically look almost indistinguishable from that horizontal line. Remember, changing the material of the bar just means changing the value of our constant C. So if I put in a larger value of C, like 2, that's going to slow the convergence. So now if we do this with this new bar with different material, the animation is going to be slower. So after 4 seconds, it won't get as far in the animation as the previous one did. I'm sorry, I said that backwards. I put a bigger value of C, so it was faster convergence, so it converged faster. If we want to see a slower convergence, we would put in a smaller number than 1, like 0.5. Because remember, when the C squared appears in the e to the minus term with the time in it, so putting a smaller number makes that exponential decay in time slower. So different material may not conduct heat energy as quickly, so it would take longer before it stabilizes. So after 4 seconds, it only got to this point.